this lecture, we are going to discuss Raman spectroscopy, which is yet another very important tool for understanding carbon materials. So Raman spectroscopy is often used as a supplementary technique or support technique with X-ray diffraction when it comes to large-scale carbon materials. So when we want to understand, for example, how a carbon material is converting from disordered carbon to, how it is gaining more order or graphitic content. But in the case of nanoscale carbon materials, it is sometimes even used as an independent, the only characterization technique. So why? Because when we have single layer graphene, or bilayer graphene or multi-layer graphene, it's very difficult to to separate them, to differentiate between them. Okay, even the transmission electron microscope may not give you the information that is reliable. So there is a possibility of error in multiple techniques. But Raman spectroscopy is the only technique which can very nicely tell you the difference between single and bilayer graphene. In fact, there is significant difference between the peaks, the intensity of the peaks that you get in Raman spectroscopy. So in that case, it is used extensively. In this lecture, we might not go too much into the details of the the Raman spectrum of graphene. I'll tell you the fundamental things, but we may not go into too much detail because the materials that are more important in this particular course are the bulk carbon materials. So we'll be focusing more on the Raman spectrum of graphite and of disordered carbons and the origin of some of the peaks. Let's see how much we can cover and how much we can understand. So we start with the very fundamental aspect. What is the fundamental principle of Raman spectroscopy? That is known as the Raman effect. Okay, what is Raman effect? Well, whenever we provide a certain energy to an electron or to a molecule, molecules are always vibrating. You probably know this. All the molecules, it's not that they are stationary. It's not that if you have a 6-membered ring that is just, always staying like that. No, it is always vibrating. Okay, so whenever we provide some energy using, let's say, a photon, then what we are doing is we are actually interfering with this vibration, the natural vibration. So there will be some frequency, natural frequency of the vibration for every molecule, which is the characteristic of that molecule, of that material, which is dependent on not just the chemical structure, but also the geometry of the crystal and so on. So that is what actually gives you the information about the molecule. So molecules are vibrating with a certain energy, and what we do is we now provide some external energy using a photon. So we are sort of interfering with the vibrational modes of the molecule, and because of that, some electrons get excited to a higher energy state, and then they come back. When they come back, they lose some radiation. That is what we measure. That is what we basically call Raman spectroscopy. So this is a fundamental principle. Okay, so let's try to understand this with this simple diagram. So I have drawn these 3 lines here. These are basically your states of the electron. So 0 is the ground state. Okay, there is energy. Okay, your electron is sitting at the ground state, and there is this some virtual state. I will tell you what is a virtual state, but before that, let's provide some energy to the electron. Okay, so when we have how do we provide energy? We take a laser. We take a laser which has some photons. Okay, and then this energy is provided to the electron. It takes some of it, and whatever happened, the interference with the vibration, we'll also learn a little bit more about that. So now this electron goes to some state that we don't know, and that's why we call it a virtual state. Basically, virtual state is also not just one state. It can be multiple states. The idea is that we don't exactly know that what is this. So it goes up a little bit. It can be little bit here, little bit there, here, but there is some sort of band of virtual states. So this is where our electron goes, and now it comes back. When it comes back without losing or gaining any energy, then we call it Rayleigh scattering. So you will also get Rayleigh scattering from the molecule. In fact, that is the more prominent one. So this is known as Rayleigh scattering. But what can also happen? You can imagine this. What can also happen is your electron did not come back to its original ground state, but rather it gained some energy. So it came back, but to a slightly higher energy state. What also can happen is your electron actually gave some of its energy to the photon, so it lost some of its energy, and it now came back to, in fact, even lower than what was its ground energy state. Okay, so both of these scattering pathways are also possible. They are known as Stokes lines or anti-Stokes line, also known as Stokes-Raman, anti-Stokes-Raman, because this is what, the idea of Raman effect is that we can measure these Stokes and anti-Stokes lines. And what we also can measure is this difference in the energy. So in fact, it is always whatever is the addition, whatever is the gain of in energy, in the case of Stokes lines, pretty much the same is the loss in the energy in the case of anti-Stokes line. And how do we measure this delta E, this difference in energy? Well, we can measure one of the two lines, and we know the energy of the ground state atom. That we know, the energy of the Rayleigh scattering, that we know how, because that is same as the energy that you provided by the photon, right? So you see that there's no change in the state of the electron. Then basically whatever energy we provided is the energy of the Rayleigh scattering. Okay, so this is the fundamental principle of Raman effect. Okay, so well, I told you all molecules vibrate. So now what are we exactly doing here? We provide some energy using the photons, but these photons, what they actually do, they change the polarizability of the molecule. So polarizability is a property I hope you understand. I'll also provide some references later on. But what we are doing is we are actually changing, we are playing with this polarizability. When we change the polarizability, what happens? This induces a dipole moment. So this is an induced dipole moment. In some other spectroscopic techniques, you just have a dipole moment, but here we are inducing it. And because of this, there are some radiations that is what we gain because of this process that is happening, that the excitation of the electrons coming back of the electrons. Because of this induced dipole moment, we get some of these radiations which could be in both Rayleigh and Stokes anti-Stokes region. So this is what we get. So now we get a sort of a lot of scattered radiations. And what we can do is we can have a filter. So this is a basic schematic of a Raman spectrometer. So you can have a filter where you can now get rid of the Rayleigh light, because Rayleigh light anyway, we know that this is the same energy as the excitation energy, so that we can filter out very easily. And then whatever we can plot Stokes and anti-Stokes. In some cases, some molecules will give you more Stokes line, some will give you more anti-Stokes line. That again will depend on the characteristic of the material, and then we detect it and we plot it, and that is how we get the Raman spectrum. Okay, you will also often hear that this is a form of inelastic scattering. Raman scattering itself is inelastic. So what do we call elastic and inelastic? If you think in terms of collisions, when two balls collide, if they do not lose any energy, then we call them elastic. And if they lose some energy, then we call it inelastic. So here there is no collision or anything, but the fact that in the case of Raman spectroscopy or Raman effect, you either lose or gain some energy. So this is known as the inelastic scattering. Okay, so now let us move on to the Raman spectrum of graphite. So we'll first talk about 3D graphite, as we always do, and because all of our materials are related to it. Okay, so all of you probably know that graphite single crystal has a B6H type symmetry. Okay, what you may not know is that it has different vibrational modes. So there are 6 vibrational modes. There are 2 E2G modes. So I will not go into the details of the explanation of these modes, but you can probably from chemistry courses, from chemical spectroscopy courses, you can definitely learn more about the symmetry in molecules. Okay, so what we have is 2 E2G modes, and this I have written with the bold letters because these are the modes that are Raman active. So basically, your molecule will have different types of vibrations, but not all of them will actually give you the Stokes and anti-Stokes type of scattering. So some of the modes are what is known as Raman active, and they are also sometimes called these are the modes that are allowed in Raman spectroscopy. So these are the 6. So 2 E2G modes, 2 B2G modes, and 1 E1U. And 1 A2U. So you can read it from here. So these are the vibrational modes. Okay. So now this is where we come to how our spectrum looks. Okay. So these E2G modes are Raman active. So that basically means they'll give you some Stokes or anti-Stokes lines. The first E2G mode, that also gives you some spectrum, but that is at very, very low wave numbers. What is a wave number? That is an inverse of your wavelength, and typically we write it in the units of centimeter inverse. So you can also use any length unit. You can call it nanometer inverse, but the convention is that we write it in centimeter inverse. Okay, so now the first E2G mode also gives you some spectrum, but that is at very, very low wave numbers, 42 or something. This is very low, and we typically don't see it in a Raman spectrum. What we do see, and that is what is known as the signature peak for graphitic carbons in Raman spectroscopy, is the second E2G modes, the intensity that is the result of the second E2G vibrational mode, that gives you what is known as the G band at approximately 1581 centimeter inverse. Okay. This is called the G band because of the fact that it is a characteristic graphite peak. So for G, people often use the term graphite band. Okay, so this is the G band, which you will pretty much always see in your, as long as your material is even slightly graphitic. In fact, sometimes even if it is very highly disordered and very little graphitic content is present, still you will see this is a very dominant peak. So you will see it. Okay, so how do you get this peak? So we were talking about the vibrations of the molecule. So this is how they want it. So this is one 6-membered ring, right? And you see these red arrows. They tell you this is how. This is sort of a translational motion. And this is how your molecule vibrates. What is very interesting about this peak is that even though it is called graphitic peak and it's a signature of graphite and so on, this is actually present in all sp2 carbons. It is actually a characteristic peak, which is this kind of vibrational mode is characteristic of sp2 type carbons, sp2 sites. When we say sp2 sites, that means there are some sp2 hybridized carbon atoms connected to each other. So basically any sp2 site, even in the polymer, will give you this kind of vibrational mode. So you do call it graphitic, but it's not necessarily just because you see this this band, that doesn't mean you have graphite in your material. Okay, so turbostratic carbons definitely will give you some graphitic, some G band, but even polymers, even anything that contains these chain-like structures which have sp2 sites, sp2 hybridized atoms, will actually give you this G band. Okay, now there is another band which is rather found in graphite and graphene. Like this is more in the purer the materials that are closer to graphite. You will also see them in disordered carbon, but not in highly disordered carbon. You will not see this peak. So this is at around 2720 centimeter inverse. This is what is sometimes called as the higher order peak of the higher order D band. I will tell you what is it. This is a peak which is very interesting. We call it G prime. We also sometimes call it 2D overtone, and we call it overtone basically means second order in the context of Raman spectroscopy. So this is also sometimes known as a second order because of the fact that it is a 2-photon process, unlike the other processes. So this is a 2-photon process, and this is also something that you observe in your graphite Raman spectrum. Okay, yeah, so this is how it kind of looks like. This is a hand-drawn spectrum, so don't expect accuracy here. But just to let you know that what we have here is at 1581 you have the G band, and that is often, in the case of graphite, definitely it's very sharp. And often it has a very high intensity compared to most of the other bands. And then 2720 or 2724 you will get this relatively shorter but still sharp enough peak in the case of graphene and graphite. So when you have less disorder in the material. Okay, fine. So basically what is happening here, especially why we can also get some very interesting results for graphene like materials and also graphene, the pure graphene, is again because of pi band. So our pi band and the unhybridized p orbital, the electron in that p orbital, and the fact that it is delocalized and it forms an electron cloud. That is, I told you that for most of the interesting properties of graphitic carbons, that is the band, or those pi electrons are actually responsible. So definitely also in this case, in the case of Raman spectroscopy, it becomes even more important because Raman spectroscopy really deals with excitation of electrons, the movement of electrons, the vibration of the overall molecule. So there, the fact that we have this sort of, a delocalized pi band present, that can influence the virtual states of your molecule or of your electron. In fact, in some cases, when we are talking about this G prime band, the electron does not even go into a virtual state. It remains in the real states, but so whatever energy the electron gains, rather than going very high up in the virtual state, what it does, it gets lost in the cloud. It goes to the real state of, let's say, a neighboring neighboring atom, or it sort of within the pi band, it stays there, and then it comes back. So it actually is staying in the real state, not going into the virtual state at all. And that is why we call it a G prime band, and that is also when people want to differentiate between G prime and 2D overtone. Then the primary difference is that if you call it a second order process, but you still are thinking that the atom or the electron is going into the virtual state, but that is not the case. It is not going into the virtual state, it just goes into another real state and comes back, and that is why it's more accurate to call it G prime. There are minor differences between these two bands, G prime and 2D. But these are the things that are still being investigated. Okay. So yeah, here is what happens. The electron gets excited but stays in the pi band. This is something specifically I'm talking about G prime band, not all other peaks. This is particularly about this 2-photon process. And now what we get from here, so when this the electron which went into some other real states, but it did come back, and when it came back, then we had some Stokes or anti-Stokes lines, and that is what we could measure, and that is the reason we get this second peak. Okay, now this is something I already told you, that G band does not really mean that you have graphite in your material, and you'll see it from all the sp2 type sites, sp2 type of carbon materials. Another interesting thing about the Raman spectrum of all sp2 type materials is that even if your material has a reasonably high degree of disorder, or let's say you're trying to do Raman spectroscopy of some diamond-like carbon film. So in the case of diamond-like carbon, we have both diamond and graphite type of sites. So you have sp3 and sp2 sites. In fact, Raman spectroscopy is often used for differentiating between sp2 and 3 sites. Even in those cases when you have significant amount of non-sp2 sites, the spectrum is often dominated by the peaks that are generated due to the sp2 sites. So this is something very important, and this is something very interesting. That is why a lot of studies are going on to understand that sometimes even when we have very little disorder, so we should not see any peak for disorder. Still we see it. Similarly, at the same time, when we have very little graphitic content in the material, which is a highly disordered material, still we do see a peak for G band. The intensity does not linearly decrease. So these are actually very interesting things about the Raman spectroscopy or Raman behavior of graphite. Okay, so on this slide, now you can see the different vibrational modes of graphite and also those of graphene. You can also call these phonon modes. So the red arrows show actually how the atoms, or what are the directions in which the atoms move, and that is why you have this overall vibration. What is very interesting, so I have drawn this image from this from a review article from Andrea Ferrari, which you should definitely read. I'll also towards the end provide some other reading material, because you see we cannot cover all the aspects, especially the aspects related to graphene and the physics behind it. We cannot cover all of them in this particular lecture. So the interesting part is how the vibrational modes of graphene and graphite are related, because we initially started learning about graphite and then we moved on to graphitic or disordered carbons. So we have not yet talked about the disorder. So we moved on from graphite to disordered carbons to carbon nanomaterials. And that is because all the vibrational modes of these graphene layers, they are connected, because you see on the left hand side how the graphene vibrational modes give rise to a large scale vibration in your AbAbA crystal. And probably from these images you can also understand there are certain modes that are only in plane. So that are only related to your basal planes, while there are some other planes which have also two layers connected. So A and B layers connected. That somehow there is an influence. Okay. So which ones will you observe in non-graphitizing carbons or turbostratic carbons, and which one you should observe only when you have perfect graphite present? Okay. So these are the different vibrational modes. Now, not all of them are active in Raman spectroscopy. Okay, so some of them are also active in IR spectroscopy, infrared spectroscopy. So what is, by the way, what happens in infrared? So we've not discussed that. Sometimes you will perform infrared spectroscopy to understand the functional groups, surface functional groups on, let's say, activated carbons. So what happens in the case of IR is that when you remember this from the previous slide, you remember that we have this energy level 0 and we have energy level 1 and -1 and so on. So if the molecule just absorbs the energy of the photon and goes to level 1 from 0 to 1, and then nothing happens, no radiation is, nothing comes back. Why? Because the molecule has actually absorbed the radiation, it has just gained that energy. So that is what happens in the case of IR spectroscopy, and that is why also it is sometimes called IR absorption. So because the molecule actually or the electron actually absorbs the energy of the photon. Okay, so what is also interesting is that in the case of a symmetric molecule, or when you have the center of symmetry present, in the case of such molecules, not just graphene or graphite, but any other molecule, as long as you have the axis of symmetry present, the modes that are active in Raman spectroscopy are not active in IR, and also the other way around. So sometimes, in the case of graphene, you see that you may have both IR and Raman activity, but when you have graphite, then some modes are IR active, some modes are Raman active, and some more modes are also active in both, but in that case you don't have the axis of symmetry present. So okay, so now you can see these different modes. What is interesting is that, so we also already discussed that only E to G modes are allowed in Raman. So I have shown it with the circle. So these are the two modes that are, that are allowed in Raman spectroscopy. Okay. Yeah. So this is something we already discussed, that you can use Raman spectroscopy to understand graphene. Now we come to the disordered carbons. So disordered carbons are interesting to us, right? We don't always have graphite. When we are doing manufacturing, we definitely, it's rare to have, perfect graphite. Okay, so we understand, again, the effect of heat treatment using Raman spectroscopy. This is very, very common. How do we do that? So now we need to have some additional band which shows that your material is disordered, right? It turns out that we do have some other additional peak, which is a result of the disorder in the material. We call it the D peak, and it comes at around 1350 centimeter inverse. It may not always be at 1350. Okay, this band, we call it D band, and often the term D is related to disorder. So you can call it a disorder band. You will also read the term defect band. Okay, okay. Actually, it originated from diamond, but it is the D band. Okay. Now this band is, it is basically, the origin of this band have been studied a lot. The origins of why do we have the D band? Okay, because it's not, it shifts its position. It also does not its intensity does not linearly increase with the increase in disorder, but however, in certain region you can have a relatively linear increase in the intensity. But there are interesting things about the D band which we probably still don't know all of them. Okay, this is known as the A1G breathing mode. So here I have shown, this is the motion of your atoms in the hexagonal rings. So this is what is your breathing mode. Okay, and this gives rise to the D band. However, what is very interesting, that this D band is activated by the presence of hexagonal rings, which means that if your material is 100% disordered, which is a hypothetical situation, does not really happen to manufacturing material at least, but if your carbon were to be 100% disordered, let's say it can also be diamond, right, and which does not have any six-membered rings, it's not disordered, but it does not have sp2 type or six-membered ring structures. In that case, you will have no D band in principle. Okay, and that is why it's also not correct to call it diamond band, but this is the history, this is how it started. The point is that this mode is due to the presence of non-sp2 sites, but it is activated by the presence of sp2 sites, and that is the reason also it does not necessarily linearly increase all the time, because there are two factors that are influencing it. One is the presence of disorder, and two is also the presence of graphitic regions, or sp2 regions. Okay. This mode is known as dispersive, or it is dispersive. What does it mean to have a dispersive mode in Raman spectroscopy? If you change the wavelength of the excitation laser, then in that case the position of the D band changes. That is what we call dispersive band. Okay. The most common wavelengths that are used for excitation in the case of Raman spectroscopy are between 515 514.5 nanometer and 632 nanometer. These are the most common ones. Okay, so if you move from 515 to 632, in that case you will the position and even the intensity of your D band can change. That does not happen to the G band. G band remains there, but this particular band is dispersive. Okay, but there are exceptions. This does not happen so much in the case of UV excitation. So the entire process slightly differs when you have UV excitation. So often you don't use UV. But if you want to understand your material, or you want to also understand Raman spectroscopy itself, then you might want to use the UV excitation. Probably, you can even go to higher energy excitation, see what happens. Okay, so yeah. A typical spectrum of a disordered carbon would look something like this. Okay, 1350 and 1580, 1581. That is what you have. These two, basically, these two prominent peaks you will have in your material. So D band and G band, they are often merged. So this spectrum could be of a glass-like carbon. This could be also of an activated carbon or porous carbon, or any some type of even diamond-like films can give you, diamond-like carbon films can also give you this kind of spectrum. So the two peaks are quite merged together and it's difficult to separate them, but this is what you see as the signature peak. Okay. All right. So yeah, there is also the second order. So I have shown this in the first order and second order peaks, and that's why I separated them. So the second order will have your G prime or the 2D overtone peak at around 2700. So this is the overall spectrum. Okay. So yeah, I told you that initially we thought that even SP, because non-SP2 sites will give you the D band. It was called the diamond band, but now we call it typically we call it disordered band. Okay. Yeah, this can now disordered band can you already know that anything that is non-SP2 can give rise to the disordered band. So it could be SP3 sites as well. It could also be any non-SP2 sites. So we know that in our carbon materials we have these SP2 plus N-type hybridization also. In that case also you can get this kind of peak. Okay. Now I told you that what is challenging here is the integration of these two peaks, because these two peaks are often merged. So what you need to do is you need to use certain software, and then you need to sort of fit these curves. And the fitting parameters can actually make a lot of difference, because often in order to understand the increase in graphitization, the one important parameter that you use is the intensity difference between the D and the G band. So that is known as ID by IG. Okay. Now again, the calculation of D and G, the intensities, can be done just based on the height of the peaks, or it can also be done based on the area of the peak in some cases. So in that case, these little calculations can make actually a lot of difference to what you understand of your material. Okay. Raman spectrum is also you could potentially calculate the crystallite size, but you can already see that in the case of graphite like graphitic carbons, it is already difficult to have these, to fit the parameters. And in addition to that, sometimes this has also been reported when the crystallite size is too small, then the calculations methods may not work. So typically for manufacturing materials, you will not calculate LA or LC for that matter using Raman spectroscopy. For that purpose, you will use X-ray diffraction. Okay. Fine. So yeah, in general, the peak integration is challenging. So Raman spectrum looks very simple, but its interpretation is not very simple, and especially understanding its origin. Because whenever we are trying to characterize something, we want to understand what is the origin of this kind of peak, right? And in the case of Raman spectroscopy, we still don't completely understand the molecular behavior. And we still we do understand now a lot of things about it, but we still if you change minor things in your material, and you can you expect sometimes the Raman spectrum to change, but it does not change. and sometimes you don't expect it to change, but it does. So these kind of things are still there when it comes to Raman spectrum. Okay, so now let us briefly talk about the other possible peaks in your Raman spectrum of carbon, and also the applications, some of the applications. Okay, this is another hand-drawn spectrum, and please do not scale it, and I suggest that don't use it anywhere else as an example, because this is just just to show you the positions of the peaks, and in fact in some cases I have just made the peaks bigger just to show you that they come at those positions. But some of these peaks are very, very small, so often they are merged also with the other peaks, and you may not see them. Okay. So other than, so you see that around 1300, 1350, you have the D band, and then you have 1580, you have the G band. So in this particular case, the D band is very strong, but you often get these two peaks merged, and you don't get the D band so strong compared to the, let's say if it is a highly disordered carbon or something. Then after that, you see this very small D prime band, which is often merged with the D band, or you will just see slight shape change in of your D band. That could be due to this D prime band, and then you can see all other potential peaks. The G prime or 2D band that I have shown here may not be as strong and sharp as it looks, because you see the material is highly disordered. But these are just the positions of the possible peaks in your if you are analyzing a disordered carbon material. Okay. What are the applications? We know, I mean, we use it for characterizing the material when we are performing the heat treatment. So this is definitely one application. Other than that, it is also very interesting when you have intercalation compounds. Intercalation means you have these two layers of your graphite, right? If something goes inside and comes out. So let's say there is some little ball which goes inside my hands. These are the two layers. So this is your intercalation, Okay. So intercalation compounds basically cause some deformation or some curls, and sometimes also defects in your material. So defects can be very nicely understood by Raman spectroscopy, but of course in that case your starting material should not have the defect. So you cannot understand intercalation materials, or you can, but it will be very difficult to understand intercalation behavior in the case of disordered carbons, because you already have a lot of defects because of the disordered carbons. The characteristic defects, and then you will also induce some more defect because of intercalation. So either you need to completely understand or your defects that are induced should be completely different from the already present defects. In that case maybe you can understand, otherwise it's difficult. But in the case of pure graphite, definitely you can understand the intercalation compounds very well using Raman spectroscopy. Okay, what else can you do? It is a heat treatment of annealed carbon is fine, but also for understanding the defects in carbon fibers. So it's difficult to understand surface defects or differentiate between surface defects and the defects that are under the surface in the core of the carbon fibers using X-ray diffraction or other techniques. But Raman spectroscopy only, it is only, let's say, 1 micrometer of your top surface, sometimes even less than 1 micrometer is what is analyzed using Raman spectroscopy. So that is also something you need to remember. So in that case, whatever are the surface defects, you can differentiate between surface and core defects of carbon fiber. So this is also that is why industrially it is used for this purpose as well. Okay. Yes. So one interesting thing is that I have told you before that this Raman spectroscopy is very simple, and we also can perform the experiments very easily. Also, you don't need to worry about the substrate very much. You can take a material inside a polythene bag, and then you can just take the Raman spectrum at various places. Also, the setup is not, compared to many other techniques, not terribly expensive. You just need a laser source. In fact, if you think about the original work that was done by Raman, he just used sunlight as his source of photons. So this is a simple technique in principle. Also, the spectra look very simple, but what is more complicated is the interpretation, and if you understand the origin of each peak. So when you analyze a Raman spectrum, try to understand why do you get a certain peak, and why don't you see too much change in your material when you make minor changes to your when you make changes to your material. Why don't they completely reflect in your Raman spectrum? So the origins of all of these the Raman behavior of the molecule is what is very interesting and also reasonably complex, and that is why it is a topic of research. definitely should read at least some of these papers, the first one is a book, but the rest of them are publications. The last one I have mentioned here is the original paper on Raman effect by C.V. Raman and Krishnan. So all of these things you should definitely read, and yeah, we can probably find out if, some new techniques related to Raman spectroscopy. In fact, many such techniques are already available, but perhaps this spectroscopy still has a lot of scope for improvement when it comes to characterizing carbon materials.